First time closing every incriminating window.
Surely. You don't want to share your screen without warning.
So now I just go back.
Yeah.
Okay, you see my screen, good. And then I'll go to
full screen mode and yeah.
Yeah. There we go. Is that full screen?
Yeah, absolutely. So it's 8:30. Prashant, should we start?
Yeah, please.
Yeah, can we start? Okay, so of course, so we are starting on time. So welcome to the special talk for QIQT 2022, which is being given by Professor Barry Sanders. Well, of course, Barry does not need much of an introduction, but because it's a special talk, I think I will do, the honors and read a little bit about his several achievements. So Barry is an co-chair of Quantum Information Science and director of the Institute for Quantum Science and Technology at University of Calgary. He is especially well known for seminal contributions to theories of quantum limited measurement, highly non-classical light, practical quantum cryptography, and optical implementations of quantum information tasks. His current research interests include quantum resources and also optical and atomic implementations of quantum information tasks and protocols. Now I'll go through a little bit of the list of various fellowships and things like that. So he's a fellow of the Institute of Physics UK, the Optical Society of America, the Australian Institute of Physics, and the American Physical Society, a past president of the Australian Optical Society, current secretary treasurer of the American Physical Society Topical Group on Quantum Information, vice chair of the Canadian Association of Physicists Division of Atomic and Molecular Physics and Photonic Interactions, member of the American Institute of Physics Education Advisory Committee and advisory board member for optics communications. In addition, Barry serves as on numerous conference committees for the APS, the International Society for Optical Engineering, Optical Society of America, and various quantum information conferences. So I don't know how much of it you actually remember because it's really a long list and it's a condensed list. But then, of course, the long and short of it that Barry is actually a towering figure in the field of quantum optics and quantum information. And it's, of course, my great pleasure to welcome him for the special talk of QIQT 2022 on observing a changing Hilbert space in a product. So the floor is yours, Barry. So we have 50 minutes for the talk and 10 minutes for questions. That is how we have scheduled this. Yeah.
Okay, thanks, Prabhashi. Thanks to everyone thanks Prasanna for the invitation to be able to speak. And I'm sorry I'm missing a lot of talks because my time zone doesn't mesh with yours. So it's your late evening and my early morning here. Okay, here's the way I'd like to, let me tell you first. Yeah, so it's about observing a changing Hilbert space inner product, and I'll make that clear as we go through. This work is done with my PhD student, Shalini Karavati, who's just wrapping up her PhD these days, and Abhijit Alasi is a postdoc in my group who's also moving on. Both of them are leaving in August, unfortunately. They've been great members of the group. Our work, most of what I talk about is in a recent publication. You can see this Physical Review research article. It came out in January, and that is much of our work, but we've pushed forward since then. And in particular, at the end, I'll talk about our experimental collaboration to, if we're going to talk about observing a changing inner product, we'd really like to see that. We actually want to observe it. So I'll tell you a bit about that at the end. And now, before I distract you with very full slides, I'll tell you a story that will help you stay clear and focused on what's being revealed here. So we learn when we're undergraduates studying quantum mechanics, we learn something like a physical state is represented by a ray in Hilbert space. And then if we delve deeper, not all of us choose to, but if we delve deeper, we discover that Hilbert space is a complex, complete inner product space. And so it means that it's a vector space and it's imbued with an inner product, and every Cauchy sequence, every sequence of inner products that converges to a point includes the point in the inner product, and that property allows us to deal with infinite dimensions. So it has an inner product. What we don't learn is that the inner product is not unique. So why is that? Why in quantum mechanics do we teach that it's got an inner product and then we leave it at that? And just to make it clear, and it'll come clear as I go through the slides, typically we'll write a state as a ket sign. And then if we can make that a function of X, or we can make it a column vector of complex numbers. Let's say we make it a column vector of complex numbers. Then when we work out the inner product or the norm, we take the column vector and we replace it by a row vector and do a complex conjugate of the elements. That procedure is what the inner product is about. It just, in a way, it just tells you how to turn kets into bras. And that's not unique. And so we do it in one particular way. And in recent years, we learned that the reason that we don't worry about which inner product we pick is because we could choose a different inner product, one that is axiomatically consistent with quantum mechanics, and still get all the same answers. And I'll go into this in some detail. But I think the reason that we don't worry about inner product too much is because if we change the inner product, we will still get the same answers with respect to what we see in experiment. So that's known. The question that I'm asking here is, what happens if it changes? So suppose that you wake up in the morning to do an experiment and the inner product is, there's an inner product in Hilbert-space. But by the time you go to sleep at night, the inner product has changed. So you wake up in the morning, you have breakfast, you prepare your states. And then in the evening, before you retire for the night, you do your measurements. But the inner product has changed between one and the other. What would happen? Is this allowed by quantum mechanics? And what would happen? And I'm going to argue that it's allowed, that it has observable consequences that could change. And when I say it's allowed, I'm going to go into a little bit into the mathematical foundations. And then when I say it's allowed, I'm going to tweak one axiom of quantum mechanics. And I need to go into the Cstar algebra formulation. And the reason I go into the Cstar algebra formulation, this is something most physicists, theoretical or experimental, don't learn necessarily, because we like to think that operators in quantum mechanics are matrices or are derivatives, but they're abstract objects that obey some algebraic properties. And then we prove that we can write matrices to represent them. So I need to get a little bit mathematical, because I have to show that different representations satisfy the same algebra. So I want to show you that I can change the inner product, but not change the fundamental algebraic properties for the system. Okay, so that's what we're going to do here. And then I'm going to start going into some detail, and and then I hope everybody follows. Okay, so here's just a table of contents slide. So I'm going to introduce the topic, give you some background, tell you our approach, give you the results, and then go to conclusions. And you can see at the top of the slides what stage we're at. You can see I'm reachable on social media in a lot of ways. So if you need to find me, there I am. And in the upper right, you can see a picture of Calgary. So it's a city, 1.5 million people. This is where I live. In the background, it's the Rocky Mountains. That's the Bow River snaking through the city. And it's a very famously a clean city. Rarely any air pollution, no, the water in the river is drinkable, etc. So it's a nice picture and it's a nice place to live. So I'm just sharing that with you. Okay, let's go through. This slide is just going to give you formally what I'm saying my presentation's about. So in order to explain to you what this is about, let's just get a bit more formal about what Hilbert-space is. I'm going to abbreviate inner product as IP, quantum mechanics is QM, and I'll use Q as an abbreviation for quantum. And so Hilbert-space, I like to think about it as the pair. So I'll use the script H to represent Hilbert-space, a script V to represent the vector space, and script I to represent the inner product. And the inner product has the property that it takes a pair of vectors drawn from the Cartesian product of V with itself. So that's script V cross script V, and it maps it to a complex number. And there are axiomatic properties of inner product that I don't spell out here, but this is the way that we do it. And then the vector space elements of the vector space we typically write as kets. So you can see drawn from the Cartesian product of V with itself, a pair of kets. And so the first one is ket phi, the second one is ket psi. And when we do the inner product, we do what I said in my introduction before I went to the slides. We turned the first ket into a bra, and then we calculate the overlap. So we might say that ket psi is a column vector of complex numbers. Bra phi, ket phi is also a vector of complex numbers, and then we just turn it to a row vector and take the complex conjugate, and then we do the dot between the row and the column vector. This is what we're used to from undergraduate days. And that's fine. This is what we're going to change, and I'm going to argue that this is illegal to change that, and I'm going to argue why it's important to consider changing it. So ket psi, and I'll get clearer later, but you can think of ket psi as just a description of preparation. So in the way I think about it, and this is the way we think about it in operational quantum mechanics, is ket psi is just a description of preparation. So if I say to you, the electron is spin up, then that assumes that we have a shared language so that we understand what that means. So if we're going to do it in the lab, then we understand that there's a source of electrons. There could be magnetic fields. There's a time scale to make sure that the orient is spin up, so lifting an energy degeneracy, making spin up lower energy, whatever it is. When I write down the term ket psi is just a code written in a language that we can mutually understand for how to prepare the system to match what we've written in our description. If you accept what I say, then you'll realize that there's a problem if anybody says prepare a state, because the state is the description of preparation. So what I'm saying is correct, but it's also weird because it doesn't allow me to say prepare a state. It is the description of preparation. And then bra phi is a description of measurement. And there's many interpretations of quantum mechanics, and one is the two-state vector formalism, championed by people like Yakir Aharonov. And the idea there, which is certainly consistent with quantum mechanics, is that every measurement is just preparation backwards in time. And so, we can think about it like that the bra phi is just a time-reversed ket psi. And I'm being a little bit sloppy, but sometimes you can think of the inner product as telling us how to convert from preparation to measurement. And so the mathematical process of turning a column vector to a row vector and taking a complex conjugate can be of that type. Okay, so then if I ask the question about whether I'm going to measure phi, if I prepare psi, then I calculate the inner product. That's what it tells me. I get a complex number, but then the Born interpretation tells me to take the mod square of that, and that will give me the probability. And the inner product has two properties. It's got norm, and norm and angle. So the property of the inner product between phi and psi is telling me that I've got some norm that tells me a probability for an outcome, and it's got an angle that doesn't make sense classically, but quantumly it means that states are not orthogonal. So there's an angle between them. Okay, and then what I'm saying here is that quantum mechanics doesn't yet formally address the consequences of a changing inner product. So this is the novelty of our work, is that we're actually saying that it's consistent to have inner product change between morning and evening. And our aim, and now this is a key point. So our aim is to establish a framework for changing the inner product between preparation and measurement. So you can prepare in the morning and measure in the evening, or you could prepare on the Earth and measure on the moon. It doesn't matter when I talk about this, whether it's spatial or temporal. And I said, establish a quantum mechanic consistent framework. So my belief, and Shalini and Abhijit's belief, is that changing inner product is consistent with quantum mechanics. And I'm going to show you literature in a different context and language that suggests the otherwise. So when I say that we're establishing it as a framework consistent with quantum mechanics, there are hints of arguments in the literature that it might not be consistent. And so, I'm showing my values here. There's no reason to believe it should be consistent, but in my heart of hearts, I think it is. Okay, So why is it even important to ask this question? Now, at the bottom, you'll see a set of references. And let me just explain how I reference. So reference one, you see, I'll move my mouse, you can see 10/B2MXRR. So you probably know that the world is digitizing references to all papers, and you put your DOI on it. The DOI is a digital object identifier. It's run by doi.org, and then they run a hash service. So it's a short URL type of service, and there you can do the short form of every DOI. It's up to maximum 6 alphanumeric characters, and it always starts with 10/. So when I write 10/B2MXRR, that's just shorthand for the DOI. So if you go to doi.org and type that in, you can find the paper. So every paper is referenced in that way. And then I just put the list of authors in brackets. Okay, so now when I refer to it, you just know how to look it up. Okay, so the first block here says, is changing the inner product consistent with quantum mechanics? So I said when I had the previous slide up that I believe the answer is yes. Now I'm just posing it as a rhetorical question. So here, let's make sure we're clear what changing means. This is why it's written in quotes. So if we say that changing inner product would be, let's solve everything quantum mechanically with one inner product, then let's change the inner product mathematically, but use it throughout every calculation, then the answer could be no. And so the idea that it changes over time and space is not yet addressed, but the idea that it just changes because you choose to redo your calculations, that is addressed. And why is it important? So here, I mentioned hermitizing quasi-Hermitian and exact PT symmetric Hamiltonians. So I'll go into this more later, but there's a big field going on in quantum mechanics now related to what's called PT symmetric quantum mechanics. And then we have closed, PT symmetric, open, exact, not exact, different flavors of PT symmetry, but it's a big topic. And you could read a good journal like Nature Physics, Phys Rev Letters, and you can see lots of experiments and people who've dedicated their careers to doing PT symmetric quantum mechanics. It's a variation of quantum mechanics. But what is that variation? So, and I'll get clear later what it means to be exact, but there's PT symmetric quantum mechanics and exact PT symmetric quantum mechanics. And what's known depends on whether the adjective is there or not. So reference one, there's Schultz, Geyer, Hanna's paper, and also Mostafazadeh. And the message in those papers is that the PT symmetric Hamiltonian literature, quasi-hermeticity, whatever you want to call it, is consistent with quantum mechanics. It is quantum mechanics. And this is interesting because we say something like, you learn in quantum mechanics that the Hamiltonian is Hermitian, i.e. the Hamiltonian matrix is equal to the complex conjugate of its transpose. More abstractly, we learn that the operator is self-adjoint, and they're not the same thing, but we often convey to students that they are, but they're not, and that's an important part of what I'm presenting here. So we know that if you don't change the inner product with respect to time or space, and the inner product satisfies certain properties, then it's ordinary quantum mechanics. There's no difference. So then the question is, what if we allow it to change over space and time? Could it be advantageous? And so in the just gotta change, oops. Okay, so you can see here that we can ask the question, and there's two examples. These aren't the only ones in the literature, but the ones that I bring up. And so the first one is about quantum cloning. The second one is about quantum computing. The cloning one, actually, I was involved with this work. So there's a reference to is by Zhang Wang, Xiao Bian, Zhang Mi, Zhang and Shui. And this is the group of Shui Peng at Beijing Computational Science Center. So she did an experiment where both in the PT symmetric context and in the context of by Urbashi, I see a hand up. Should we do something about it now?
I think, Barry, I was just typing that it is best to keep the questions till the end, because otherwise we may not, it may
Okay,
interrupt
either
the
way.
flow. You're okay with it? Then we can, sort of encourage it.
Yeah, I'm okay with being interrupted and I don't have to get to the end.
So if you're okay, then Stephen James, you can ask your question. Stephen, do you realize that you have your hand up? Okay. I think he's
sorry,
unmuted. Yeah.
actually it was by mistake, sorry.
I lowered his hand. I've got co-host privilege, so if they don't respond fast, there's another hand up.
Rohan Chakravarti.
Yeah, isn't a part of the definition of the inner product that it's invariant under any transformation and linear transformation? So what exactly do you mean by changing inner products?
Well, I'll get to it. I'm just telling you the story at the moment, and then I'm going to get mathematical later. The problem, Rohan, is if I tell you too much, if I get too technical, I'll lose people. So just give me a few slides and then you'll see. Okay.
Okay.
And so, Barry, in the chat window, we also have this confusion that they're not getting how inner product can be prepared physically. And so maybe you will also answer that as you go along.
Yeah. Okay. I appreciate the enthusiasm. Let me get to it. I'm building up a story. So you know how you can buy a novel or you can buy short stories, and this is a novel. So just be patient with me.
Sure.
Okay. But I'll move on then. So let me get a few slides, then I'm happy to be interrupted. Okay, so the paper reference 2, I just mentioned about the paper from Shui Peng's group, and this is the idea of doing quantum cloning. And so quantum cloning has the property that that we know from a 1980s paper by Wouters and Zurek through the linearity of quantum mechanics that if you want to clone 2 arbitrary states perfectly, you can't do it. And so the idea that you can clone 2 non-orthogonal states, there are 2 directions to go with quantum cloning. One is to do what is called heralded perfect cloning. So you clone perfectly some of the time and terribly other times, but you know when it worked. And another direction for quantum cloning is you just clone badly every time. The reference 2 is consistent with the former, that it's perfect cloning some of the time. And so we allow the inner product to change and take advantage of that. And we discover and demonstrate experimentally that the perfect cloning some of the time, randomly but heralded, is consistent with inner product change. So I know some of you are impatient to get to the math, but I'm just trying to give you the sense of build up the story. So part of the story is that the heralded perfect quantum cloning is a consequence also of changing inner product. So we're getting a sense that there's some way to think about it. It doesn't change quantum mechanics, but it does give another perspective on cloning. And the idea intuitively is that, if you wake up in the morning and you have one inner product and you have 2 states that aren't orthogonal, just wait till evening. If you know by the evening they will be orthogonal, then you clone them. And then if your inner product snaps back to what it was the next morning, then it turns out to be heralded quantum cloning. And I'll go through the math. And then reference 3 is interesting. They suggest that the PT symmetry, which I'll show is equivalent to changing inner product, is faster, could be faster than Hermitian quantum mechanics. So they speculate on that. And I would say the answer is emphatically no, that I believe there's no advantage, but it's important to get the math right. And then the final block is about observing exact PT symmetry. And so we know, and this goes back to Dorje Brody's work, that the idea is that if you have a closed quantum system and the inner product doesn't change over space and time, then there's no way to see whether the inner product's different. But Brody's work talks about exact PT symmetry. And so, and this is related, like I told you, there's a vast literature on PT symmetry and it's not observable. So question that I want you to have running through your mind, if anybody knows the PT symmetry literature, is why do we even do it? Or are we doing it? And if we are doing it and it's not observable, how can we have all these experiments? So let's just put that into our shopping list of things that we want to answer. Okay. Now, the claims that we have, first of all, I have four claims. These are specific results. First of all, we've developed a framework that's consistent with quantum mechanics for allowing inner product of Hilbert-space to change. So I claim it's consistent. There's one caveat, one rule I'm breaking. And when I get to that slide, I'll put in red the change so that you won't doubt it. And then you can decide whether my claim is digestible. Second, that the changing inner product is simply a quantum operation. Now there's quantum channels are completely positive trace preserving maps. A quantum operation is a completely positive trace non-increasing map. So in order to make it consistent with quantum mechanics, I have to allow the norm to decrease. Third, that our framework is relatable to open PT symmetric dynamics. So to some extent, talking about inner product change could be another language for talking about open PT symmetric dynamics. So what I'm talking about, and I'm going to try to convince you, is it relates to that whole world of theory and experiments related to PT symmetry. And finally, if it's representable by a quantum operation, then we can use a mathematical technique called Stein-Spring dilation and say we could just add more dimensions to Hilbert space and everything, all states are pure and all maps are unitary. If we do this formally, we know this is called a dilation. If we dilate, then we would replace the Hilbert space by a new Hilbert space whose dimension is the cube of the first one. But what we discover is in order to simulate inner product change, we only need one extra dimension, we don't need to cube the dimension, we just have to add one, which is a vast savings. And it means that experimentally it becomes nice because it just involves replacing, if we deal with qubits and we think that we live in this PT symmetric universe, we can simulate it by just turning qubits into qubits. And the novelty of our work, first of all, what makes our work different from past work related to inner product change, PT symmetry, is that we separate the representations, matrices and derivatives, from the Cstar algebra, which is the star in mathematics is the dagger in physics. It's just the adjoint. And so we just take the algebra, what algebra the operators, if you think about it that way, satisfy. Cstar algebra, they're called observables. So what is the algebra and how is the star done, the adjoint? And we separate, we make sure it's consistent that way. And then we deal with the inner product change in terms of representations. And then the novelty that we have, the operationalized PT symmetry via inner product change means that we can cast the language of PT symmetric quantum mechanics as inner product change. Okay, and I know I'm sorry for those impatient to get to the math. I still want to get this background right. So here, this is 4 papers that give a context. This is not a comprehensive list, but it just gives you the idea of the field. The upper left is what I regard as the seminal paper in the field by Carl Bender and Stefan Bocher. And so this came out in 1998, and this is really the paper that launched the subject of PT symmetry. And what they did, they said, the paper title, it was Physical Review Letters 24 years ago. It says, Real Spectra in Non-Hermitian Hamiltonians Having PT Symmetry. So let's just digest what's going on. So this Physical Review Letters article is saying Hamiltonians don't have to be Hermitian. So that breaks a rule that we typically teach to students, non-Hermitian. So it means that the matrix representing the Hamiltonian is not equal to the complex conjugate of its transpose. Sorry, Sayantani, I hear a lot of noise from your side. Can you? Oh, that's muted. Oh, I hear somebody else. Okay. Anyway, I have the power to mute people, so I'll use it. Okay, real spectra, yeah. So, and then let's just be careful. So non-Hermitian Hamiltonian, they're saying provided that a non-Hermitian Hamiltonian has a spectrum that's real, then what they show is it has PT symmetry. They use the term PT taken from what we would say in particle physics, where we often say parity, but P is a point reflection symmetry. T is time reversal, but in their paper, they don't say it has to be point reflection and time reversal. I'll go into the math. They just say, provided the Hamiltonian has the P is representing any linear isometry on Hilbert space, T is any anti-linear isometry, and you put them together, then they say, given this, then there exists a non-Hermitian Hamiltonian. And I'll go through what that means. Then you can see, and this launched theory and experiment. The next paper in the history timeline that I really like in this is the one below by Ali Mostafazadeh. And he proves exact PT symmetry is equivalent to hermiticity. So you see the contradiction here, that Bender and Bocher are saying, writing this Physical Review Letters article saying, here's the physics of quantum mechanics if Hamiltonians are not Hermitian. And then Ali Mostafazadeh says, if the PT symmetry is exact, and we need to get into what that means, then a non-Hermitian Hamiltonian is Hermitian. That's a oxymoronic, right? If I tell you that night is day or black is white, sounds a contradiction. That's exactly what you see in these two titles. So they prove that exact PT symmetry is Hermitian. How do you resolve this paradox? You have to be careful what you define to be Hermitian. That goes back to the inner product. And then in the upper right, you see a paper by Dorzier-Brody, and he is saying that PT symmetric quantum mechanics, without the term exact in the title, is consistent. So he's establishing a consistency for PT symmetric quantum mechanics. So these three papers to me are very important theoretically because they give the lay of the land, but they don't complete the story yet. And so this is what we want to deal with. Oh, Urvashi.
So Barry, we have a couple of questions in the chat window. Do you want to take them?
As long as they're not mathematical yet, just if they're
they are based on ideas. So how is your idea related to open quantum systems, since we could have non-Hermitian operators in open systems?
Well, how's it? In the experiments that simulate PT symmetry, they use open systems in the following way. So what I mentioned is you can simulate a PT symmetric system by adding dimensions to Hilbert space. It's a dilation. Open systems do exactly that. So if you open your system, you bring in extra dimensions of Hilbert space. So there's a relation that I'll get into, like I'm only answering conceptually. This is all going to become clear in the talk. But adding dimensions to Hilbert space could, not necessarily, but could be done by adding extra dimensions. And this is typically the experimental approach.
And that probably answers this following question. Is it possible to visualize more than two-dimensional vector space?
Depends how good your vision is.
But then I think you're going to talk about increasing the dimension and
yeah, but if you ask me about visualizing, okay, we normally think we live in a three-dimensional world. So, if we ignore curvature, space-time, and all those things, let's just say we live in a flat three-dimensional universe. That's a three-dimensional vector space. I can visualize it.
Okay, so I think we will go on with the talk then.
Okay. And sorry, probably there's something meant, but for anybody who knows me or Bashi can testify, I take everything very literally. So if you ask me about how to visualize more than two dimensions, I just think Euclidean space and visualize it. So I'm very happy to take questions, but just be patient with me because I'll take everything literally. Okay. And then the lower right is just a chance to brag about my own work. And that's the experimental cloning in a pseudo-unitary system. This one we are dealing with. There's a language of pseudo-unitary, quasi. I forget. There's various terms, and they get mixed up. But in this one, we talk about a pseudo-unitary system. And so, if anybody's interested in the experimental side, this is a nice one to take a look at. It's this is the one about the cloning where we change the inner product and we wind up getting realizing random heralded perfect cloning. Perfect is up to experimental error. Okay, now for those who want to see the math, I'm going to start getting mathematical. So first of all, let's define PT. So the PT is not the particle physics type PT, but rather Bender and Bocher generalize it. So P is any linear isometry on H. And so a linear isometry, unitary operators are isometries. It's just inner product preserving. So P is an inner product preserving map. And linear means that the operator acting on the sum of kets is the sum of the operator in each ket. T is an anti-linear isometry, which means it preserves the inner product, but the action of T on a sum of kets is the sum of T on each ket, but the coefficients are complex conjugated. And so we can write any linear and any anti-linear isometry denoted by P and T. They have to square to be the identity and they have to commute with each other. And so that's our definition of P and T. And then the particle physics P and T satisfy those. Now, the next thing is to define what we mean by a Hamiltonian given P and T and a PT symmetric Hamiltonian. So this is consistent with literature. So let's say you take quantum mechanics and then you write down on a piece of paper your description of P and T, and you write down a description of the Hamiltonian H then if you say to me, is my H PT symmetric? Then I would compose P and T to get PT as one operator. And then I would check whether it commutes with H. If it commutes, then I decide that you gave me a PT symmetric Hamiltonian. And if it doesn't commute, then I say, sorry, didn't work. It's not a PT symmetric Hamiltonian. So that's the way I think about this coming. And the way I'm posing it and the order of operations and the questions are important because the literature is a bit confusing. And by getting all this clear, we can cut through it and understand. And I've made a point of separating PT symmetric from exact PT symmetric. And here I say exact PT symmetry corresponds to HPT and PT sharing all eigenvectors. And then I say that it's exact PT symmetric if all eigenvalues of HPT are real. And by the way, I never said that H had to be self-adjoint. So if you write down a Hamiltonian description on a piece of paper and hand it to me, and you say, is this a PT symmetric Hamiltonian? I don't care if it doesn't have to be self-adjoint. It's more interesting if it isn't. Now, notice here that I say share all eigenvectors, so the eigenvalues are real. I'm going to go back a slide. Notice here, Bender and Bocher write real spectra. And I'm not saying the word spectrum, I'm saying the word eigenvalues. Why am I doing that? It's because when you go to infinite dimensional Hilbert space, there are issues that arise in separating eigenvalues from spectrum. Finite dimension, they're equivalent. So we want to make sure that we get everything right, even for infinite dimensions. So we need to be careful on changing inner product in the infinite dimensional case, and I won't get into that here. Okay, and then the result by Mostavazadeh can be understood very briefly, but this is, so the way that we're building everything up gives us very short proofs of what's already known. And I'm going to stick to finite dimensional Hilbert space. And you can see it says M is in B of H. So script H is the Hilbert space. B of H is just a set of bounded trace class operators on H. And so M in this case is in B of H just means it's an operator on Hilbert space. So mathematically it would be homomorphism. We'll use the physics term, which is linear operator. So if I'm talking about an object in bounded trace class operators on the Hilbert space, I'll call it an operator. If I'm talking about the Cstar algebra with observables, I won't use the term operator. So I'm going to separate the two, and we need to because the Hilbert space can change inner product. So the idea that exact PT symmetry is quasi-hermiticity just works as follows. This is summarizing Mostavazadeh. For all finite dimensional diagonalizable exact PT symmetric Hamiltonians, and everything is defined above, there exists a metric operator. So eta is a metric operator. It's self-adjoint, it's positive, and if we redefine the dagger, instead of saying that the dagger of H is the complex conjugate of the transpose, we conjugate it. By conjugate, I mean I put the inverse on the left and the eta on the right. So I conjugate by this metric operator, then I can, if I redefine hermiticity in that way, then the HPT is Hermitian. And so back to here, this is what Mostavazadeh is showing, is he's saying, don't use the dagger of Bender and Bocher, redefine the dagger with respect to this positive definite metric operator that we know always exists. And the metric operator is an inner product operator. So we know an inner product induces a metric. In relativity, we often talk about a metric when we think about an inner product. So I'm calling it a metric operator, but it's really an inner product operator. But in the spirit of theoretical physics, we just when we talk about inner products, we often talk about metrics. So it's just a way that we use our language. Okay, now I want to go to the operational approach to quantum mechanics because we need to allow that inner product to change. So let me just give you some basics of Cstar algebra. There's nothing here more than what we need to have our discussion. So it's, for those not so mathematical, there's things to think about, but I'm trying not to make it complicated. And I promised you I'd put in red what I changed. So it's important we go through this. So first of all, a Cstar algebra comprises observables. They're self-adjoint under the star operation. As I said, star is the dagger in quantum mechanics, but I'm going to use the star for the adjoint at the algebraic level and the dagger for the adjoint at the operator level. So dagger is going to be used for conjugating an operator. Star is going to be used for conjugating the algebraic element. I want to separate the two. So I'm using both the physics and the mathematics notation. Now, and the algebra, if you just put in your mind something like Pauli operators. Oh, another question.
Shall we take that, Barry?
Up to you. I don't know what the question is.
Yeah. So Shorin, do you want to go ahead?
Yeah. The question is, I think I got the definitions you gave, but the status of Hamiltonian in quantum mechanics is that it generates time evolution. Now, in whatever definition you gave, where is that hidden? That what is your prescription of time evolution, given all the definitions you gave?
So that'll come up, but I'll answer because I want to make sure everybody's following. So
Okay.
Good question.
Okay, fine.
No, fine. I'm saying I'm complimenting you on asking the question, and I'm going to give a short answer, and it'll become clear later.
Okay.
So yes, the Hamiltonian generates time evolution, and yes, that will change. And I'll show an explicit expression yet later. So when you think of a time evolution, if you have a time-independent Hamiltonian, then you exponentiate it and solve it. If you do a time-dependent, you do a time-ordered exponential, time-ordered product for the exponential. But that's not the end of the story. When you want to figure out what happened in an experiment, you generate your time evolution and then you measure. And so it's the combination of the evolution changes, the measurement changes, and this will be in the last block on the slide, they cancel out. So that's a short answer. Let me explain it.
Thank you. Okay.
But Shorin, your question, allows me to give more context. Like in this first block, I'm talking about states because, and this is why the star is there in C-star algebras. We want to say, what are the observables and what are the states that correspond? Earlier, I talked about a state as a ket, but now I'm not talking about it that way. So states are linear functionals on the algebra. So I said, if we take Pauli, let's just think of Pauli matrices, Pauli operators. So Pauli operators refer to how to change a spin-half system, and the matrices are a representation of how to do it. And then, but they're different, right? The Pauli operators satisfy some algebra. I said I wouldn't call them operators of their algebra, but I guess I'm doing it. So there's the Pauli operators, they're defined by the algebra, then the matrices are representations of them. And then we have the state. What is, it's a spin-half system. As I said before, it could be spin up, spin down, spin plus, whatever. And states are just linear functionals that act on A. So it means that if, and we represent it by the set omega, and omega is the linear functional. So what you see here, suppose that A is, let's say it's sigma plus, it's the raising operator for a spin-half system. Sigma plus star is sigma minus. So now I can say, what is the expectation value for observing? So I'm going to lower your hand, Shorin. There we go. Nice having this power. So we have linear functionals. Okay, so we have A star A would be sigma plus sigma minus, say, or sigma minus sigma plus. And then we say, what is the expectation value? And that's what this tells us how to do. And in C-star algebra, we say, provided that omega acts on a self-adjoint entity, then there's a non-negativity. And it says omega of the identity is equal to 1. And here I'm saying omega of the identity is less than or equal to 1. So this is the key point, is I'm saying I'm allowing quantum mechanics to change by saying the norm of a state doesn't have to be 1. It can be upper bounded by 1. And so that's the tweak. So when I say that inner product change is consistent with quantum mechanics, I'm breaking a rule, but I'm claiming that this rule change makes a consistent quantum mechanics. And I feel justified in doing it because if PT symmetric quantum mechanics is justified and consistent, I actually need to break the rule. So I don't feel I'm breaking a rule, I feel I'm improving a rule. Okay, now how do we go between states and observables? The answer is in mathematics, mathematical physics, we use the Gelfand-Neymark-Siegel construction, the GNS construction. And this construction is just a very formal way of saying what I said earlier, turn a ket into a bra. And so the GNS construction just says, first of all, if we take an algebra element, so think of a Pauli operator, and we turn it into an operator on Hilbert-space, so we can think about some matrix representation, pi is doing this. So pi is what allows us to go from the algebra to the matrices or derivatives or whatever. So pi is the representation map. And then the S is the set of states, and I'm introducing a notation here, the sharp symbol, which is red. Sharp is used in mathematical physics for pullbacks. So I'm using this consistent with how it's done in mathematical physics, but it's never, as far as we know, me, Shalini, Abhijit, it's never been done this way before. So I'm putting it in red, not that I'm introducing a term, but I'm introducing a symbol into Cstar algebra that wasn't used in this way before. So I'm just letting you know that. So this is the idea that we could turn operators to states, and that sharp pi is essentially telling us how to turn kets to bras or whatever. So if the ket is a state and bra is related to operators, well, operators are bra kets. So it's just telling me how to turn, it's telling me how to turn bras to kets, that kind of thing. Okay, so this is saying, given an operator, I could turn it to a state under that sharp pi map. And then the pi, which is the representation, has the property that the representation of the conjugate of an element of the algebra is the conjugate of the representation of A. This is, so in physics, we use the same thing. We say, if I take sigma plus dagger, I get sigma minus. And if I write the matrix, I say dagger tells me to take the Hermitian conjugate, and we think they're the same thing, so we use the same dagger. The reason I'm changing it is because if we change the inner product, then we won't change the conjugate at the algebraic level, but we do.
Please mute your mic. Yeah, very go on.
That was scary. Okay, so then we change it that way. Maybe just as a matter of etiquette, maybe Urbash, you could just remind everybody that they should be muted. So.
Yeah, of course, everyone other than Barry should be muted during the talk, right?
And you.
Yeah, obviously I am.
Okay, so that's the idea. And then the sharp pi we can think of as follows. So in the second bullet, in a textbook, now this gets more advanced. People here seem to know open systems. So we could talk about a density matrix or a density operator rho and omega. And so sharp pi is really the idea that rho is an operator version of the state, and omega is the functional, and they're related by that sharp pi map. So, and then the way I think about it, and I'll show you in a moment, is, if I say, what is the outcome of a measurement? I say trace of rho m, where m is the observable, but the trace rho together is the omega. So the omega includes not just the operator, but also the procedure, the tracing. And so sharp pi of rho would say, okay, if rho is the state given as an operator, omega is trace rho blank. And you'll see that in the last block. And a pure omega can be represented by an operator, which would be kept psi brop psi, but we're starting to doubt what brop psi is, under pi. So then the idea now is that we're going to change the representation. So H, the Hilbert space we see is a vector space with inner product. We keep the vector space the same, we change the inner product. And the idea that quantum mechanics doesn't change under change of inner product if it's static is the idea that at the algebraic level, changing inner product to Hilbert space doesn't matter. But it does matter here, and so I allow pi to be one mapping from the algebra to the, if you like, matrices. Pi prime is the other mapping, and the idea that they're observationally indistinguishable, which emerges out of work by Mostafazadeh and Brody, is simply can be seen as follows. And this relates to the question by Shorn about the evolution. So what happens here is if we change the inner product, then the representation of the operator, that's the representation, traced with rho, the inner product changes both rho and the representation of the algebraic element, and the two changes cancel each other out through that GNS construction. So this is a one-line proof of essentially what Dorje Brody is showing. The reason that we can't observe a different inner product is because we have to change the state and the operator the same way. And this relates to the question about the unitary evolution. It's if you change your Hamiltonian, that's only half the story. You have to change the states too, and they change consistently. So my question of what happens if inner product changes between morning and evening is you have one in the morning when you have rho, and the evening when you do your measurement, the inner product is changed. This no longer holds. We would have a different prime on each and it wouldn't change. How am I doing for time?
Barry, we are at the 50-minute mark, but because we had interruptions, do you think you can wrap up in 7 or 8 minutes?
Yeah, I can stop immediately.
No, but
That's
that
easy.
won't be very.
Exactly. I didn't
Yeah.
get to the story. Okay, so that's the idea. Yeah. And okay, so this slide I don't need to go through. This is simply saying, well, bottom part I don't need to go through. This is simply saying that we have a new inner product. So we don't change the vector space, but we do change the inner product. And the new inner product is labeled by that metric operator eta, and it is done in the following way. It just says, if we take the inner product as turning a cat to a bra, all we do is make it a sandwich. We just say, we now replace the inner product between phi and psi by putting this metric operator. It's the same kind of thing we do in relativity. We just, you can change the metric in that system. So we just say that the inner product change is the change of a metric that way. This I won't go through, obviously we don't have time. And this is simply telling you that the pi map, that if we change the inner product between morning and evening, it's a well-defined process. We break it up to show, we do another conjugation. The importance of conjugations mathematically is that conjugating a product is the product of conjugation. So it's important to do it that way. And then we just prove sum, product, and star consistency. And we introduce a dagger if we don't change the inner product and a double dagger if we do. So we have different symbols here for conjugation under different inner products. And this slide is just showing you consistency. This slide, in this slide, we start using the notation of category theory, which probably almost no one or no one in the audience knows, and it's not important. We don't make use of subtle category stuff. We just make use of the diagrams. And the message in this slide is simply as follows, that if we change the Hilbert-space inner product under I eta, so this is the new inner product, then if we go to the operators, we write that as a completely positive trace non-increasing map, which is the quantum operation. That's what it's defined to be. And if we go under our sharp pi, the pullback to the states, then we have the conjugate of that quantum operation that maps states to states. So we're able to say an inner product change corresponds to this quantum operation. And we prove all that here. And essentially the quantum operation just has two parts. One is decreasing norm. And if it decreases, it doesn't have to decrease, but it can decrease the norm. And the other part is to change the angle. That's what allows the cloning, is that the non-orthogonal states can become orthogonal later on. And then what does it mean to observe it? Well, so I'm just going to be more mathematical, and I'm just going to say, if we can perform process tomography on the change, then it's observable. So the idea is that if every day the inner product changes the same way from morning to evening, you just set up your experiments every day and you do process tomography on it and you discover that change. And then down here, we just show how to implement it. This was the question that came up later. What came up earlier by Sharon is, what is the evolution? Well, the evolution follows the same rules. We just exponentiate the Hamiltonian. It is no longer Hermitian, so we need to be careful. We have to build in kappa, which is the inverse of the norm of the inverse of the metric operator. And this is essentially a way of tracking how the norm decreases. So what it means practically, this is why the open system questions came up, is because in order to make it consistent, we have to throw stuff away. Now, people who do open systems say that means an open system. Actually, it doesn't. You can mathematically consistently talk about throwing things away without opening the system. You open the system because you want conservation. So if I say I threw away particles and there's a conservation law, I need an open system. But if I break the conservation law, then I'm allowed to throw things away and don't worry about it. I can throw away. Yeah, that's the idea. So we can play around with that. This is simply just making all the math consistent so that we have inner product change. We know what it does to cats and we know what it does to quantum operations. And this part I won't get to, I just put the slide up, but this is our experimental approach of embedding in a QTRIT. And we essentially came up with a set of properties for, we describe how to simulate the whole thing with respect to QTRITs. And we're collaborating with one of the quantum computing companies where it turns out that the qubits are really QDITs. And so we're making use of extra levels to be able to simulate. We've been working on this for over a year now, and it's hard because once you start looking at the QDIT properties of commercial quantum computers, they're a bit subtle. And there's my conclusion slide, and I'll turn it back to you, Arbashi.
Thanks, Barry, for this very nice and very comprehensive talk. So we have lots of questions in the chat window. Before we go to the chat window, can we have the questions by, people raising hands? So Aniket, do you want to go first? Aniket Patra. While Aniket tries to unmute himself, Shorin, do you want to go with your second question? Then I'll go to the chat window.
Well, I can unmute him. Just give me a
You
sec.
can, but then maybe he's not raised it knowingly. So we'll wait.
Oh,
he cannot
yeah,
unmute.
I was
Yeah,
not able to
Shorin, go.
unmute. Finally, I did. So I have another question, which is, see, the way we write the non-Hermitian time evolution, it seems to be something which is a invertible map. On the other hand, let's say when you are doing it in Bloodian, it's a non-invertible map. Now, where is this subtlety? But you did mention that you can think of it as open quantum system. But if it is a Markovian open quantum system, then I believe it becomes non-invertible. So how should I look at it? Maybe.
No, that's good.
Okay.
So let me go through this. So if you know the Lindbladian, by the way, we don't call it Lindbladian anymore. It's something Gorini, Kosakovsky, Lindblad.
Sorry. Sure.
And there's more letters added as people discover more things. No, I appreciate it. So I've given up. I just call it a quantum master equation, and I know what you mean. So what happens is I'm giving you a quantum mechanics that's a closed system description. So there's no Lindbladian, if you like. But I also talked about simulation. So there's a way to take the quantum master equation, and then what we can say, instead of saying there's a Hamiltonian and then there's the Lindblad terms, we can say there's a non-Hermitian Hamiltonian, and then we just add the jump terms to preserve norm. And if I'm telling you that the norm can change, I would throw away the jump terms. So, and then I'm saying, okay, let's throw away the jump terms. Is it then consistent with quantum mechanics? And then the answer is yes, provided that that's due to an inner product change. So what I'm saying to you is that there's a consistent way to look at this where we say we don't have, like when you talk about Markovian, so there's three assumptions in the quantum master equation. It's Born, Markov, and weak coupling. That's all related to make it consistent with an open system. I don't need that. The other thing I said here is we don't have to go to a quantum master equation. I said something important, but very quickly, that all we do is have to add one more extra dimension. So instead of going to an open system description, I'm saying, let's take a system, we'll just deal with finite dimensional, let's say it's a QDIT system. Now, if I change the inner product, I can simulate it where I have, instead of the QDIT of dimension D, I have a QDIT of dimension D+1. So there's a lot going on. I don't have time to explain it all fully, but your approach to thinking about a master equation, quantum master equation, allows you to think of a way of simulating the inner product change. It is not that, and it's actually an inefficient way to simulate it. You're using more dimensions of Hilbert space than you need to.
Okay, thank you.
Thanks, Shorin. Aniket, do you want to now try?
Yes, I can unmute as well. So my question was with this regarding this metric that you introduced. So I was wondering whether this is a dynamical object or not, in the sense that I think you just mentioned in reply to Sorin's question that in some sense, this is like those, I can think of these as the jumps. So is that a correct way of thinking about them?
So you're asking me more than one thing. So you asked me about dynamic metric operator, and then you asked about jumps. So let me take it as two different aspects. So in what I described, I just say something like, you get up in the morning with one inner product, you go to sleep with the other, and all I care about is the map from morning to evening. It's perfectly reasonable to say, how does it change during the day? And that's how I interpret your question about dynamic. And the answer is, it should be able to. We just haven't solved all that yet. And it's because it becomes composability. So if you have a map of how the inner product changes from morning to evening, then you can say, well, how does it change minute by minute? And then we have to make sure that we are able to do the minute by minute changes, that they compose, that it is well behaved in the limit that minutes go to seconds, go to microseconds, go to Planck scale, whatever. So there's a lot of consistency tests. So your question is excellent. It's something we just haven't done yet. I've got a little bit of preliminary work done by an undergraduate in Calgary. So we are getting the words of composability right. But your simple question, the answer is it should be described dynamically, but there's a lot of things to get right. And it's not easy to get right because in the quantum mechanics literature, we tend to merge various concepts. We have to disentangle these concepts. The second part, oh, go ahead.
Sorry, just to follow up. So this dynamics, do you expect it to be unique?
Well, so I turn back to slide 6, and at the bottom you say for all finite dimensional diagonalizable exact PT symmetric HP, there exists eta equals eta dagger. It's not, doesn't have to be unique. So we have to be, so it's another way of saying if the inner product changed between morning and night, it could change in different ways. So we could have, it could be not changing for 10 minutes and then change for 10 minutes. Or it could have changed in the first 10 minutes, or it could change less in the first, change throughout at a slower rate. So no, it's not unique at all.
Right. Now I'm just thinking in terms of metric in maybe GR. And so whether you have a geodesic of some sort, something like that.
You're right. This is, so the way you're thinking about GR, in GR, you can, obviously this is not GR, but this is geometrizing what's going on. And then we're doing the shortcut. We're just saying, we don't know what goes on in between, but yeah, playing around with metrics and allowing to modify is what comes into play here. Exactly. I agree.
Okay.
Barry, do you have 5 more minutes or because we are at the 1 hour mark?
I do, sure.
Yeah, so then we'll take some questions from the chat because there are quite a few enthusiastic questions. So one of them is it possible to solve the Shannon information entropy for any PT symmetric potential?
Well, okay, so let's see if I get the question. First of all, Shannon information is purely classical. There's a Halevo extension. So I guess I'm gonna, because I want to connect with quantum mechanics, I'll interpret the question as being a quantum version of Shannon. So can you read the question again?
So is it possible to solve the Shannon information entropy for any PT symmetric potential?
Okay, and I warn people I'm literal. So
There's a problem then, yeah.
Well, no, the question is it possible to show something? If the claim is not true, then it won't be possible. So the question's not well posed in my way of thinking.
Yeah, because I don't know how you can solve the entropy. I mean,
yeah. And I mean, there's a limit to how much I can interpret. So the question is, I've decided it's not a well posed question. I'm sorry to say.
Sure. So then we go to the next one. You've shown these short forms and you explained that quite well about how you're showing your references. But then people are wondering if they can still get the conventional way of referencing through email if they were to email you or something like that.
Well, if somebody, like I just said, you just type the 10/whatever into doi.org, I can show it. So, but the question was whether they can, they can email me, but I might be scathing in my response saying, I explained it. So why don't I just explain again? You just go to doi.org and then you type in 10/B2MXR. You can do it now if you're at a computer, just test it out. But
well, they have to be at some sort of a computing device to listen to you right now.
No, well, they are. Yeah, they have to be at one now.
Yeah.
But I don't know the
So they can try it for the next 1 minute and while we go through the next question. So I think you made a comment during the talk that when H is not self-adjoint, it gets more interesting. So the question is, why do you think it's more interesting to be not self-adjoint?
Well, that goes back to here. This is, it goes back to this motivation that well, one reason it gets more interesting, as I said, like there's this whole literature on PT symmetry. So, you can go to Nature Physics almost every issue and see somebody do an experiment. All they're doing is saying, I've designed a system that has a non-Hermitian Hamiltonian. Maybe I'll just take a moment and explain what happened. So, because I've been involved in some of those experiments. And so, typically experiments are done optically. And then what happens is, so what we do is we say, we simulate PT symmetric system by saying, let's have losses in an optical system. And that's easy to do because every real experiment has losses. But then what you do is you say, let's plug in two amounts of losses. Let's put in big lossy terms and little lossy terms. And then let's pretend that the loss is more than the little lossy terms would give. So what is loss in the experiment becomes noiseless gain in a mathematical description. And so by balancing loss with noiseless gain through this trick, we managed to do a PT symmetric system. This is simulating an inner product change. So if an experiment where you put two different types of losses and call it noiseless gain and say that you're doing PT symmetric quantum mechanics is interesting, then dealing with non-Hermitian Hamiltonians is interesting. So like, I don't know, I'm getting old. So I'm at the point where almost nothing is interesting to me, I'm sorry to say. And so my claim of it being interesting is saying, if you find X interesting, then Y is interesting. That's the nature of my argument.
It's a logical deduction kind of argument.
Yeah. So what other people find interesting, that I'm saying, if you find PT symmetric quantum mechanics interesting, then you must find my work interesting. But if you don't find it interesting, then my work is not interesting either, I would guess.
Right. And that leads to the next question as to whether you can say something about these things physically or experimentally.
Yeah, and that's what I just did. So
right. So I think that answers the question.
Well, but I'll just mention, I mentioned the loss noiseless gain interpretation, but also the Q trick, just take it. I mean, that's what I find more interesting is all I do, like I'm part of me is a QDIT person. So, if I take, which Urvashi knows because she's a QDIT person too. So we're two QDITs in the same meeting, and maybe there's more. And so the idea that I can just say, well, all I do is just elevate the dimension of a QDIT, I find interesting, that I don't need to go to the whole open system. So in my world where almost nothing is interesting, the statement that I can understand it by just elevating the dimension of QDIT is one of the rare moments in my life these days where I actually find what I say interesting.
Yeah, we won't get into the details of that one. So there's one more question about what if all observables are quasi-Hermitian but not PT symmetric?
So let's look at the title of this. So, okay, I won't go into the details of non-Hermitian, quasi-Hermitian, pseudo-Hermitian. There's all the words around and subtleties. But it says this is about exact PT symmetry, that the Hamiltonian is not Hermitian, but it has PT symmetry and therefore has a real spectrum. So if that all holds, then we have consistent quantum mechanics. We don't have to, and to my mind, it's just an inner product change subtlety. So, but then if you start saying, what if we drop another condition? Well, if you start dropping too many conditions, then you don't have normal quantum mechanics anymore. And I would dare say it's not consistent. I would say you didn't invent a new quantum mechanics, you just, and this is where, like I said, about faster than Hermitian questions, and there's other literature out there where people draw conclusions I think are incorrect, is they failed to account for all the requirements. They sometimes start saying, well, if I drop this rule, it's interesting. It's not interesting. It's inconsistent. That's not interesting, is my argument.
Is it possible to observe the change in inner product for non-Hermitian Hamiltonians other than PT symmetric systems, like systems defined on curved space?
Provided it satisfies the mathematical axiom. So in curved space, I'll interpret that to be curved space-time. So it's a GR question again. The idea is that, well, I mean, it's a tough question because we haven't reconciled quantum mechanics and general relativity together. Right. So maybe the nonlinearity of general relativity could be explained by an inner product change. I don't really know. Like, what I'm interested here is stretching quantum mechanics to its full capability. I love the question. Like, I would like to say, please pay attention to me because maybe this will solve the problem of reconciling the two and it's related, but I'm not that kind of person. So I don't know, but it's really an interesting question. And this came up in the verbal questions earlier, can I think about it related to GR? And these are all tantalizing questions and I have no idea how to deal with them, but they're interesting questions.
So we'll take a break from the chat and go on to Apurva Shorkar. Do you want to unmute? Because he's raised hand. Knowingly?
I've asked him to unmute. That should help.
Yeah.
Oh, he's
muted again.
Maybe I asked, maybe we did two operations that canceled. In fact, he disappeared altogether now.
No, he's around. He's muted. So we'll wait for him. So is there any loophole in pure PT symmetric quantum mechanics?
Oh, okay. Now I have to interpret. So the word loophole usually makes me think of Bell inequality. Is that
Surely, because it's related to the first talk of QIQT this time, which was by me.
right?
So I think there
Yeah.
is a connection there. So yeah.
Is there any loophole?
Mhm.
I mean, so I would say the question about a loophole in quantum mechanics doesn't make sense.
Mhm.
So the
Yeah.
loopholes come up when we say something like, let's take, what was it? Objective reality. What's the term? Local
Realism.
Yeah, local realism. That's the word. I forgot the word realism.
Mhm.
Yeah. So we take a local realistic description, and then we do an experiment. We say we tested local realism, and then you discover that there's a random sampling hypothesis, and the superdeterminism, and blah blah blah. So the loopholes all come into things like local realistic attempts to describe quantum mechanics and drawing a conclusion. So, but everything I'm doing, what you'd have to do is come up with a local realistic description of PT symmetric quantum mechanics. And then you might come up with the idea of loopholes. But I don't know any literature on a local.
Can I add to that? Can I add to that answer, if I may?
Please.
Yeah. So, I mean, you're saying, the loopholes come in when you actually can come up with some interpretation of your result, which is explained by something other than what you think you're actually trying to do. And so here you're trying to sort of do an experiment or, motivate an experiment in your case on pure PT symmetric quantum mechanics. So the question is that, is this sort of an assumption really? I would interpret the question this way, that is this purity of the PT symmetric quantum mechanics an assumption and requirement for your experiment to succeed? Or, can there be another way of explaining our ongoing experimental results, which actually even, have some ambiguity associated with them? So that is the sort of I think the motivation behind such a question. A loophole need not be associated with just local realist inequalities, of course.
Yeah, okay.
Any quantum optics experiment can have a loophole, right? Yeah.
Okay, so if I think about it, the question broadly, and I said that if the norm decreases, there's a loss allowed.
Mm-hmm.
So in testing local realism versus quantum mechanics, that's the random sampling hypothesis. It's the difference between the CH and the CHSH inequality. And then if I say to you that losses are allowed in my system and they occur randomly, and there's no open system for them to leak into, what would we compare to? Would our local realism also have a norm decrease? And so I think there's an interesting question there about how to reconcile tests of inner product changing or PT symmetric quantum mechanics where the norm decreases. How would we deal with random sampling? So the question might actually be touching on an important point of how to deal with change of norm with respect to quantum mechanics.
And there is another related question. Is it possible to prove PT symmetric quantum theory using CHSH inequality? So I think, again, related to relating these concepts with each other, right? Again, something that you just touched upon, but this is another question from a different person.
I think I know how to pose it. It's when I said that the norm decreases randomly. So I say the norm decreases in what I describe, and that was a key point I changed in the Cstar algebra. Who decides which instances to delete? So in a conspiratorial view of the universe,
absolutely, yeah,
the deletions could be manipulated to trick us. So yeah, it's a good question.
So you're actually allowing for the fair sampling loophole. In some sense, by sort of not going for a whole sampling, as you said, then it's random, so you don't know. It's a subset that you're dealing with, and the other subset could be doing something else. Okay.
Yeah, and it's not answerable in the framework, like in the framework of Cstar algebras, and then I talk about GNS construction. It's like saying we do everything with respect to probabilities, and yet when you do an experiment, you're sampling it. So it's about it's a statistics probability connection. So the framework that I introduced won't answer that question. No. It has to be, there has to be an extension to what it means to sample. Like I'm saying, outcomes are trace of rho m, that kind of thing. But that's just describing averages. And the loopholes come in by sampling distributions. So I don't know the answer.
Right. So can we have one last question? Because it could go on, but maybe you want to, I don't know how you're placed.
I got
So
nothing to do. Like if I'm a speaker, I like to talk forever. If I'm in the audience, I want it to end. So it's up to you.
I'm neither. So neither the audience nor the speaker, but I'm chairing the session. So I mean, I'll take a middle ground and allow for, let's say, 2 more questions. So we have one raised hand by Ashish Mehta. Do you want to unmute and say something? That has become an issue these days.
I just asked him to unmute formally, so maybe that'll help.
Okay, so there is a question not directly related to the talk, apparently. That can get tricky with you, Barry, but then let's try it anyway. Where does the Berry phase fit in this description? Can we have a geometric phase in this new description?
Isn't that funny? So I just got back from Australia last week and was talking to Daniel Burghardt. That's right, Daniel Burghardt from Macquarie University. He asked me the same question, and he asked me over and over. So I'm well prepared. I know, so I think I understand the question, what's coming up. It's this whole channel of quantum operations. I say you wake up in the morning with one inner product, you go to sleep with a different one, there's a metric operator associated with it. Then, if there's that change, is there a Berry phase, a Pancharatnam phase, geometric phase, whatever you want to call it? So there would be, but the problem is, and this relates to another question that came up, just a few minutes ago, about the dynamical aspect of Eta. So earlier I answered the question saying, if Eta should change dynamically, but we have to get the math right to know how to turn, the change from morning to night into minute by minute or second by second and make sure everything makes sense in the continuous time limit. And then if I want to answer the question about the geometric phase, I have to be able to separate the dynamical from the geometric property. And nothing I've done so far in this presentation, and even the work we've done so far, makes absolutely clear how the dynamic properties work, and therefore I don't know the geometric properties either. We have to understand both hand in hand.
Okay, so then we go for this one last question. So what do you mean by that we have to add a dimension instead of using the master equation in open quantum systems? How can we deal with the dissipation?
Oh, okay. So I don't say we have to. I'm not a dictator here. So you can do it. You can say, well, there's first approach is saying this quantum mechanics has non-Hermitian Hamiltonians, the PT symmetry, live with it, right? So there's no extra dimensions. You just have to live with the consequences. And that's what is in these papers, Bender and Bolker, and et cetera. They're just saying this is an alternative version of quantum mechanics. Or you can say, I don't want to live with it. I want to fix it mathematically by changing the inner product. That's what I do. And I say, it is quantum mechanics. You just picked a stupid inner product is how I'd put it in a rude kind of way. But you can do the thing you say, well, I really want to make an experiment or do something. I'm going to open my quantum system, which came up with the question. You can say, well, I just think it's an open quantum system. I'm just not smart enough to know it's open. So you can choose it. And I call that a simulation. But then I say, if you want to simulate it by opening the system, you're just bringing extra dimensions of Hilbert space, and I can make it much more affordable. Why bring in all these extra dimensions with an open system, et cetera? Why not leave it a closed system and just add one extra dimension of Hilbert space and do it that way? And so then I say to you, you can open the system. I'm not a dictator. I don't decide how to do it. But if you just add one extra dimension, isn't that a lot cheaper? So there's a whole set of choices how you do it. It's like quantum mechanics. You can have your interpretation. I got mine. We'll come up with the same answers. In this case, I see open system, adding a dimension, changing the inner product is all different ways to interpret. They have different ontologies, but they're not testable against each other. They're all given the same answers.
Mm-hmm. So I think that's a great answer. So Prashant, you have your mic unmuted.
Yeah, no, I'm just waiting for the last thing.
I think, because I think, now I would say that, if you have any further questions, they can feel free to email Barry, who may or may not answer them. But then, depending on how polite the question is, but then I think otherwise we could just go on, and maybe some people have not yet had their dinners. I don't know, because we are at 9:49, so it's a very tricky thing. So I think we can formally end this session. If you wanted to talk to Barry, you can perhaps do that after we formally end this session, Prashant. So thanks again, Barry.
I think, it's already late, and thanks a lot.
Sure.
It's a
Yes.
very excellent talk. Truly enjoyed it.
Yes. It's always, I'm hearing, I've actually chaired this same talk by Barry once.
Okay.
So it's amazing that I have actually heard a similar talk and also chaired that session. So that That's a very big coincidence, which I like in experiments as well.
Better find everything to talk about.
So yeah, absolutely. So thanks a lot, Barry. As always, it's always a pleasure listening to you, and I'm sure everyone really enjoyed and learned things from this talk. So we will formally end this session. So Prashanta, did you want to say anything further?
I just wanted to thank Barry, very nice talk, and truly enjoyed it. And hopefully you should visit India sometime, because now we are all okay, I mean, from COVID point of view. So
2,000 cases per day.
Okay, I'm not worried. I look forward to seeing you soon. I'm certainly going to look forward to coming back as soon as possible.
Absolutely. Thanks a lot, Barry. See you then. Bye.
Bye-bye.
Yeah.